Okay. Okay, so we'll start with input-output management, and we discussed some of the things in the previous class about how a device is every device has to have at least 3 addresses assigned to it, one for the command register, one for the status register, and another for the data register. And as far as operating system is concerned, either it can try to see if a device is available or not, and do it periodically, which is known as polling, or a device can send a signal to the CPU to say that it is ready. Now we will be talking about another device which is very important, a device which is used for persistent storage, and that is hard disk. So this is actually still the media with the highest storage in terms of capacity, highest storage capacity, and is persistent. So even if you switch off the light, even if the electricity is not there, the data on the hard disk will remain. And hard disk, as you know, is actually a set of circular disk platters which are mounted on a spindle connected to a motor. So when the motor rotates, when the motor is switched on, all these disk platters will rotate about this spindle. And the disk surfaces or the disk platter surfaces are coated with a magnetic material. So electromagnet can be used to read from or write to the surface. And generally when you're looking at a platter has 2 surfaces, and both the surfaces are used for reading and writing. And that is to ensure that high volume of data can be stored in the smallest possible volume. So naturally, use both the surfaces, then naturally the storage capacity is going to increase. It will be doubled actually. So now on every surface, the data is written in circular track. So it is written in circular track. In this particular case, we are showing one track, and each track is divided radially into sectors. These are the sector numbers, and the sector number will start from 0. So as far as the hard disk is concerned, it can be array of n sectors, and these sectors are numbered from 0 to n-1. So generally, when you're writing to a sector, this is atomic operation. So either it is all or none. So either the operation will be successful, or it will, or no data will be returned to the sector. But generally, if you're reading it data from a hard disk sector by sector, it can be very time consuming. So generally, the disk data transfer from hard disk to main memory is in terms of block, where a block is a contiguous chunk of multiple number of sectors, and this is to increase the data transfer rate. So if you look at the disk geometry, the disk geometry is consisting of concentric circular tracks, and each track is divided into sectors. And generally from this track, the data will be written, transferred from disk to memory, or disk to disk controller would be via a electromagnetic disk head, which is attached to an arm and move across the surface, as we will see. So this is how the structure of a hard disk is. So these are the tracks, as you can see, and the blue lines actually show the logical division of the sectors. Okay, and each disk has 2 surfaces, upper surface and lower surface, and actually there are 1 head per surface. So there is 1 head here and 1 head to read the data from the lower surface of this. And this head is moved across this arm so that it can read a particular track. And the disk is rotating at the high speed. So if the head is stationary, so what the track which is coming under the head when the disk is rotating is a circular track. Now, if you view the track, track, let's say this is track number 1, 2, 3. Generally, the outermost track is given track number 0. So if you view from the, so if you look at the track 0 of all the surfaces, then it will look like a cylinder. So a term cylinder is used to denote all the tracks which are all the tracks which are in the same position on each surface. So now if you look at the sector size in terms of the length, the sector size is largest at the outermost track, and you go from outermost to innermost track, the size of the sector will reduce. Size of the sector in terms of the space on the linear space on the disk will reduce. But because each sector will consist of the same number of bytes, it means the data density will increase as we go towards innermost track. So in the tracks which are very near to the spindle, the data density will be very high, and generally these tracks are not used for reading or writing purpose. They are not used for storage. So generally an operating system during formatting, only the outermost tracks will be used, and some of the innermost tracks will not be used. Now disk is rotating at a constant angular speed. So time to read or write data from each sector would be same. So during read and write, the head will be positioned, head will be moved along this arm to bring it to the correct track, and then it will keep on checking whether the requisite sector has come under it or not. And when the requisite sector comes, the data will be actually transferred to the disk controller. And identification of which sector has come is done through a formatting string. So when the disk is formatted, at the beginning of each sector, there will be some data which will be written to mark the number of the sectors, a sector number or sector address, and something to indicate that this is not a random data. This is not the data which is written to the disk, but is a formatting data. So formatting a disk means marking the boundaries of the sectors also. So if there is only a single track, so naturally the arm can be positioned, the head can be positioned on the track, and when you want to read the data, all you need to do is to wait till the requisite sector comes under the head. So this is known as rotational delay. So this is the time to bring requisite sector under the head. So if S is the number of sectors on the track, then the minimum rotation required in terms of the number of sector would be 1. So if I'm at sector number 6, so because the disk is rotating like this, so the next sector that I can read is 7. So the minimum delay would be for rotation of up to 1 sector. And maximum rotation would be for S-1 sectors. So if there are 12 sectors, so the maximum rotation that I may have to do is 11 sectors. On an average, the movement will be S/2, where S is the number of sectors. But now, generally, describing it in terms of number of sectors would be cumbersome. So we'll go for rotational speed. So if R is the rotational speed of motor, and this rotational speed is generally given in terms of revolutions per minute. So R is the rotation speed of motor in terms of revolutions per minute, okay? RPM. So it means in 60 seconds, the disk is moving R number of times. So in 60 seconds, the number of tracks which are transferred is equal to R. So in 1 second, so if we want to, so R number of tracks are moved in 60 seconds. So 1 track will be moved in 60 upon R second. So it means if the complete track has to be rotated, so the rotational delay will be equal to 60 upon R, but average rotational delay will be equal to 30 upon R, because it is time to move the half of the track. But if there are multiple tracks, then we may have to move the head also. For example, right now the head is reading the innermost track, and if I want to bring it to the outermost track, so there has to be some movement of the so the head has to move from this position to this position. So it has to move along its arm, and this is known as seek time. Now, if you look at rotational delay and seek time, both of them involve mechanical movement, and that's why they are very expensive in terms of time. So typically the seek time will take about 4 to 10 milliseconds. So if you look at the disk access time, it will consist of seek. First of all, you have to bring the head to the correct track. Then once it is at the correct track, you have to bring the correct sector under this, and then you have to transfer the data. So total time to access some data from the hard disk would be equal to time to seek, time to latency, and time for transfer. So if there is a sequential access, then once you have positioned the track, positioned the head on the correct track and the sector, and then you can start reading. So ultimately it is the transfer time which will be the dominant factor. But if it's random access, I'm trying to reach sector this, then sector this, then sector this, then ultimately for every sector read, I need to incur the time on seeking as well as latency. So in this particular case, these terms will be dominating. So let's look at an example. So let's say disk is rotating at 6,000 revolutions per minute, and number of sectors per track are equal to 8. So naturally, if I want to find out the average rotational delay, so 6,000 tracks are rotating in 60 minutes, or 1 minute, that is 60 seconds. So one track will be taking 60 upon 6,000 seconds, that is about 10 milliseconds. So average rotational delay will be half of this, that is 5 milliseconds. So this is the time to rotate the disk by half a track. And data transfer time, we are saying it is about 1.25 milli. How did I calculate? Okay, so in this particular case, if you look at this particular scenario, so in 10 seconds, a complete track is being transferred. So, and the track is consisting of 8 sectors. So it means data transfer time is 1.25 millisecond per sector. So if you are reading 100 sectors, then it will be about 125 millisecond. If they are continuous. If they are not continuous, then for every sector, you need to incur 5 millisecond plus seek time as a overhead. So this is an example. So this is their two specification of two most popular drives, Cheetah and Barracuda. As you can see, Cheetah is rotating at a high speed, so naturally the seek time and data transfer time will be much less in this particular case. So let's look at Cheetah. So in this particular, the latency would be, so in 60 seconds, you are transferring 15,000 tracks. So 15,000 tracks are transferred in 60 seconds. So half a track will be transferred in 2 milliseconds. And transfer time is 125 megabyte per second, and we want to transfer 16 kilobyte. So 125 megabyte can be transferred in 1 second. So 16 kilobyte will be transferred in about 0.125 millisecond. I'm here making an approximation that 1024, that is 1 kilo, is equal to 1000. So the disk access time will be equal to average seek 4 millisecond plus 2 millisecond plus 0.125 millisecond. So as you can say, compared to seek time and latency time, the transfer time is too low. This you have to do. Actually, this is not calculated. This was an assignment, so this calculation is not correct. Okay, this calculation is not correct. Okay. Now there is a problem. So if the tracks are, if the sectors are not numbered properly, then what will happen that by the time a head moves from one track to another track, because of the rotational delay, some of the sectors have already moved. So to take care of this track skew, the sector numbers are assigned in such a manner that sequential reads can be properly serviced. If you look at this particular case, the track skew is of 2. So I'm starting from 0 and 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Let's say I'm at still 0. When I come here, the track number 12 should be coming under. So I'm starting from 0 to, I've read the track number 11. So when I come back to this particular scenario, the track number 12 should be here. But the problem is that because of the skew of 2 sectors, there could be a problem. So I will not number this sector as so naturally by the time I come here, the disk has moved. So because the disk is rotating in this manner and there is a skew of 2, so by the time I come here, this sector, so before I begin to move, this particular sector was at this point, and by the time I move the head, this will come at this point. So I number my sectors to take this track skew into consideration, and this will ensure that I do not have to wait, I do not have to incur the cost of rotational delay when I move from one track to another track. So here you can see that by the time the sectors, the head starts moving from this track to this track, and by this time, whatever is here comes under this. So I will be numbering this as sector number 12, 13, 14, 15, 16, 17, 22. Similarly, after 23, so 24 will be again at this point. So naturally, one thing that you need to remember, that track skew will be slightly changing. So by the time I read this sector number 23, this sector will come here. Okay. Now track skew, now I said that all the sectors are divided radially. It means that in one angular, so the time to move a sector, to rotate a sector will be same across all the tracks. But in some cases, some of the disks are organized as, so in this particular case, the data density is changing. The data density is smallest at the outermost sector, but it is largest at the innermost sector. In some of the cases, the length of the sector is same because we keep the number of, so the data density is kept same. So if the data density is kept same, so the outer track will contain more number of sectors as compared to inner number of tracks. In that particular case, track skew will also vary from track to track. So the numbering system will be more complex. But generally, most of the modern disk will be organized in this manner that all the number of sectors per track are same. So generally, track 0 is the outermost track, and there are two ways of giving the numbers. That is surface number, track number, and sector number. And so in that particular case, if you're moving from track to track, so you will read. So if there is a contiguous allocation of the data, then first you are going for surface 0. First you are going for surface 0, then surface 1, then surface 2. Then in that particular case, there will be so read entire surface, you will be doing multiple seek time. But if you store cylinder wise, then while you are reading one cylinder, you do not require to do any seek time. So cylinder wise, so you store, so when you're storing the data contiguously, you store on cylinder 0. So surface 0, track 0, surface 1, track 0, surface 2, track 0, surface 3, track 0, surface 4, track 0, and so on and so forth. And once the tracks 0 for all the surfaces have been full, and then we move to the track number 1. So this is what this will reduce the number of seek times. But this was an older way of disk addressing, because in most of the modern systems, what operating system can tell the interface provided by the disk controller to operating system is that read this sector or write to this sector. Where actually this sector is located on the hard disk is not known to the operating system. And why it is done like that, the point is that if you're trying to write too many times to a particular area of the hard disk, or some of the sectors may go bad. So to ensure that these bad sectors do not have any adverse impact on operating system writing to the hard disk, so the disk controller will reserve some area to take care of the fact that some of the sectors might go bad. So when a sector goes bad, a sector from that reserved area will be allocated that number. So actually the sectors which are contiguous in number may not actually be contiguous on the hard disk. So because of that, the earlier way of allocating contiguous allocation cylinder wise or surface wise is no more that beneficial in case of modern drives which are hiding their geometry from the operating system. So generally this is a term, a volume. And if you look at the, we'll be coming to it again when we talk about file structures. So the idea is that we can divide a disk into multiple volumes, and one of the volume will contain the first sector of every volume will contain a master boot record, because each volume can be bootable from a different operating system. So the first sector of the volume will be master boot record, and this master boot record will contain the partition table, information on this partition, type of partition, etc., etc. And if you go to a partition, the first sector of that partition would be boot record. We'll come to it again when we talk about file structures. Generally, hard disk will have a disk controller, which will be equipped with a disk cache or the buffer. And this buffer will be actually accommodating data till it is actually returned to the hard disk. Or if the data is being read from the disk drive, then it will keep the data till this data is transferred to the memory. So there are two ways you can write the data to a hard disk. In one case, as soon as the data is received in the disk cache, the acknowledgement is set that data is returned to the hard disk. The data is not actually returned to the hard disk. The disk controller will start writing the data to the hard disk, but because this is available in the disk controller's memory or buffer, so it will acknowledge that the data has arrived. In case of write-through, the acknowledgement will be sent only when the data is actually returned to the hard disk. So in this particular case, in write-back mechanism, it is quite fast, but the problems may come if the power fails. Now the point is that disk controller will receive multiple requests from different areas of the hard disk. So either there will be read request or the write request. So in any case, it has to go to the requisite sector and start serving the request. So because the request will come into, so while it is serving one request, other requests may come. So these requests will be put into a queue, and the request will be served one by one from this queue. And this serving of the request will be known as disk scheduling. So it will use some policy to identify which request to serve first and which request can be served later. So these are the disk scheduling mechanism: first come, first served, shortest seek time first. But because seek time and rotational time both can have impact on the performance, so SSTF is a special case of SPTF. SPTF is shortest positioning time first. Then there are scan, look, and CFQ. So in first come, first served, actually, as everyone can guess, the very first request which comes will be served first. The problem in this case is that if the requests are coming in different order, then seek time may be too much. So it may have to go from some outer track to some inner track. Then it may have to move quite a lot. The disk movements will be quite high in terms of seeks. So for example, let's assume that head is at track 50, and the requests are in the these are the track numbers which are being received for the request. So now if you look at the total head movement, from 50 it has to go to 23. From 23 it will go to 34. From 34 it will go to 5. From 5 it will go to 78. From 78 it will go to 29, and so on. So the movement will be from 50 to 23, then 23 to 34, 34 to 5, 5 to 78, 78 to 29, 29 to 63, 63 to 43, 43 to 50. So the total number of seeks that will be required will be 271. So if each seek is taking 4 milliseconds, so you can see that this is an appreciable time. In shortest seek time first, you try to locate the nearest track in terms of seek time. So if I'm at 50, so the nearest track which can be served now is 43. So 43 is selected. Now I'm at 43. So from 43, either I can go to 63 or I can go to 34. So 34 is nearest. And from 34, I go to 29, 29 to 23, 23 to 5, 5 to again back to 63, and 63 to 78. So number of seeks will be, so the idea is to reduce the seek time. So this is actually a greedy approach. And because this is a greedy approach, so it may not always give you a very good answer. So anyhow. In case of scan, the disk arm will start from, let's say, outermost track and then move towards innermost track. And then from innermost, it will again go back to outermost track. So it will keep on moving back and forth like a case of lift. The elevator will go up, elevator will come down, elevator go up, elevator will come down. So while it is scanning from left to right and then again from right to left, in both the cases, the problem in the scan algorithm is that when you're starting from inner track to outermost track, when you're tracking from innermost track to outermost track, you have already served the requests which are near to the outermost track. So while you are coming back, you might not be. If you search the queue for serving the request, it will actually incur the time. So a better version of this is what is known as C-scan. In C-scan, you go from innermost to outermost and outermost to innermost, but you serve the request only during one sweep. In the reverse direction, you do not try to serve any request. So the seek time. So that it will be faster. We'll see why it is faster. So anyhow, this is a scan algorithm. So you are at tracks 50, and we are assuming that tracks are numbered from 1 to 99. So if you start from 50, go to 43, and then 43 to 34, 34 to 29, 29 to 23, 20 to 5, then go to the track number 0. And while it moves from innermost to, it will go up to outermost. So if there was any other request which was coming, so it will go up to 99 and then come back. So it will go from 0 to 99, 99 to 0, 0 to 99, 99 to 0. In case of look version, it will again go from innermost track to, it will move from innermost to outermost, but it will not go towards the outermost track. It will go to the track, maximum track number which need to be served. And then it will go from outermost to innermost and so on. So again, you have to remember that outermost track is the track number 0. Okay, so it is at track number 50. So it is starting from 50 to 40. It will go only up to 5. It will not go up to 0. It will go only up to 5 and then reverse the direction. So the variants of scan is the C-scan and C-look and step. So in case of C-scan, it will go from, let's say, innermost track to outermost track. Sorry, it will go from, let's say, outermost track to innermost track and serve the request. But while coming from innermost to outermost, it will not serve any request. So the idea is that the position of the head should be moved quickly before it starts serving the request again. And same thing is true for C-look. Another version of C-scan is n-step scan. In this particular case, you are going to serve the request in terms of batch of n request. The problem with shortest seek time first is that it is a greedy approach, but it will not work very nicely for modern disk drives because the geometry is hidden from the operating system. So it is quite possible that sector number 2 and sector number 3 may not be adjacent to each other because sector number 2 might have gone bad, and while the disk manufacturer was manufacturing the disk, so this bad sector has been actually now positioned somewhere else on the hard disk. So logically, as far as operating system is concerned, all the sectors are present, but the sectors may not be contiguous to each other. So the approximation of shortest seek time first would be the nearest block first. So the operating system can try to say, okay, these are the block numbers. So after this block number, so when the blocks are mapped to the sectors, generally blocks will be mapped to contiguous sectors. So that's how it can try to reduce the seek time. Another problem with the shortest seek time first is that if there are, if most of the requests are towards inner track, then any request from the outer tracks, they will have to keep on waiting till all the requests, because the head is at the head is towards, let's say, innermost tracks. Then head will keep on moving over these inner tracks only. It will not come to the outer track because of the greedy approach of the greedy nature of this algorithm. So it may lead to starvation. Let's say we want to serve these two requests. One is 16, sector number 16, and sector number 8. Now, if the rotation is faster than seek, if the rotation takes faster time, then and let's say we are at 30 and this is rotating at this way. If we have to bring come to the sector number 16, we have to rotate only by this. We are assuming track skew is 0, okay, right now. So when you rotate it like this, so this track will come at this point. So it will take this much time, and 8 will take this much time. Okay, 8 को यहाँ तक आने के लिए पूरा 8 will take this much time, and I think this has shown wrong. So the disk is rotating at this way. Okay, sorry. The sector is, head is at this point. So when the disk is rotating in this way, so to bring to 16, to bring near to the 16, the rotation has to take place only by this. But if I want to bring the head here, so it has to rotate up to this much. So if rotation is faster than seek, then so if rotation is faster than seek, then actually request 16 should be served before request 8. And if seek is faster than rotation, then request 8 should be served before 16. So that is the idea. So generally, SSTF is replaced by shortest positioning time first in case of modern disk, because seek and rotation approximately are the same. One of the scheduling which is implemented in Linux is completely fair queuing. C stands for C, is completely fair queuing, in which case we use a queue for each process. So the requests which are generated by the same process will be given will be stored in a separate queue, and then the disk scheduler will actually try to do a round robin between queue. So first of all, the queue for process 1 will be served, then queue for the process 2, then queue for process 3, and so on. And each process will be given some slice time, so during which the request for this process only will be served, and this slice time is proportional to the priority. And within the queue, it may try to optimize order by using first come first serve, by using shortest seek time first, and whatever. And if a process does not utilize its slice, it can yield it to the next process. So this is what is CFQ scheduling. In most of the modern modern systems, now we are coming up with solid state disks, which are more reliable because electronic read writing is used and there is no moving part. And so therefore there is no seek and rotational delay latency, and they consume less power. If you look at the hard disk, it has to be continuously rotated. It's a mechanical rotation, so it requires more power. But solid state disk will not be requiring that much power because they are basically small integrated circuits which can be operated at. They will not generate that much heat also. So they are expensive as compared to hard disk, because hard disk is just a magnetic memory, but this is a kind of flash memory, and their lifespan is shorter than hard disk because on an average you can write only as many times to a particular location. So the number of writes to a particular location is limited, let's say 10,000 or something. As a result, every block can be written only a limited number of times. So you cannot continuously write to the same area again and again. So its write algorithm will try to distribute writes to different part of the SSD. And as a result, it does not guarantee a secure deletion of the file. So this is all about our input-output device management, solid-state device, disk scheduling. Close the presentation. And Navdeep Singh, if there are any questions, you can ask me the question. I have posed the question for the attendance. Navdeep Singh. Yeah, Navdeep. Do we have some time or? Yeah, we have some time. So Navdeep, can you start your presentation on deadlock avoidance? Can you start sharing? Why are people leaving? Is the other class started? I think there's time for the other class, no? I cannot hear you. Navdeep? Yeah, now I could hear you.
Yes, ma'am. Yes, ma'am.
Yeah. Now I can hear you. Continue.
Yes, ma'am. My screen, is it visible?
Right now, I can see the chat screen, not the presentation screen. Yeah, now the presentation screen is. Yeah, continue.
Okay, ma'am. Ma'am, first of all, before going to the deadlock avoidance, we must get to know what deadlock when system is able to make this, because various of the, for simplicity here we consider only two threads. They are blocking each other by acquiring the data must to and the deletion, of course. And while we were considering the dining philosopher, the examples that were shown was if and when every philosopher picks up a chopstick, and so neither of them can proceed to eat, and neither can give up the resources without it, because there is no such condition applied, so deadlock occurs. For deadlock, from this example, we can get that deadlock do have some necessary conditions to occur. Is the mutual that is mutually excluded, that it cannot be acquired at the resources. Let's consider an example of a printer. It only print the time frame goes for various resources. System. The whole and this is why the dining philosopher becomes a trivial be discussed while we consider because the philosophers might holding one while for the and they are studying the resources which might while they are on it. Next, there is no preemption. By solution later, the of acquired by. So if somehow we can get to a rollback mechanism for preemption of the resources being held by a particular thread, deadlock might be avoided. But again, this condition still holds, and then we experience a new phenomenon called for the first this base these we can follow everyone for the on for the writing them in deadlock. Hello.
Hello. ठीक है. Okay, so let's call it a day now. If you have any questions, you can ask him. Hello.
Thank you.
Okay. So thank you for being here. So let's close the session and please answer the question on the